All right. So we were talking about this guy and our yeah yeah. So working with. Can I still see my screen? Okay.
Yes, I can.
So if you have two numerical variables x and y having at least moderate correlation, and before you can even build a linear equation between two variables x and y, at least x should be uh, correlated, like should have a significant correlation between both variables. So if that's been established through both correlation and scatter plots, the regression line is used to predict the value of y given a value of x. So you can see use the scatter plot or the correlation function to check. So for example, if you look at, so if I go to my ask studio, there's an inbuilt data set in, but let me just call it an inbuilt iris. So if I want to check the correlation between two variables now, I can use correlation iris. The first four variables are maybe I can perform a correlation. I can find correlation between these first four variables. If I should want this, I have the matrix of this form. This one is saying that this is a correlation matrix between the variables here. I have four variables: separ dot length, separ dot beta dot length, beta dot width. The correlation between a variable and itself is 1. Now, correlation value is falls between -1 to 1, -1 to +1. If it's a positive one, if it's close to a positive one, you have. If it's a 1, you say it has a perfect positive correlation. If it's a -1, it has a perfect negative. But in real life, you cannot even see two variables that are perfectly correlated. So, this a variable and itself is a perfect correlation. You are going to see a 1. So you are not checking that. Now, if you look at this guy and this guy now, petal length and sepal length, you can see they have a strong correlation, a strong positive correlation. And look at petal width and sepal length, also a strong positive correlation. If you check the correlation between petal width and petal length, you can see the correlation is very strong even compared to this one because it's very close to 1. So you can use this to check the correlation between two. So if you want to confirm this, even this guy, that petal width and petal length, for example, I can do a scatter plot. Say plot iris the sepal petal width and iris sepal petal length. If I should plot this now, you see a scatter plot, you can see that it's strong positive correlation because an increase in x, which is the petal width, causes an increase in petal length. So that's an intuition using the scatter plots. You can also use correlation to get the exact estimate in that regard. So with that in
Sorry,
mind,
but what's this data iris 1:4? I don't get what you're doing. Let me not lie.
okay, this one. So this one is because you missed some classes. That's why you didn't get what this one is saying. What this one is saying that in this iris data, this is a data frame, like a spreadsheet kind of data. So I'm saying that pick the first four columns. So
Pick
if you
what
check
the first column.
the first four columns, let me check the head of iris so that I can see what I'm seeing. So this one is going to pick the first 6 rows in the iris data set. So this is how the iris data set looks like. This is the first 6 rows. Can you see?
Okay. Head iris is to return the spreadsheet. The iris, is it like inherent, like a data inside arm?
Yeah, it's an inbuilt data set in
Inbuilt data set. Okay.
So this statement here, this is what it means. Let me run it here. It means return the first 4 columns, which is 1, 2, 3, and 4. The reason I'm not including this guy because it's a categorical variable. So 1 column 2 means 1 column 4 means 1 to 4. So the first four guys, return it, perform a correlation on it using the correlation function. Do you understand?
Yeah.
So if I should run this, you see that it's going to bring the first four column, everything, all the rows. So this is it. This is the first four columns, everything, all the rows. So that's what this command is actually doing. Okay. So yeah, just perform the correlation function on this result. So have a look at it. Okay. Do you understand now?
Yeah, I do.
Okay. So this is the normal regression formula. This is your y-intercept, and this m is your gradient, this y is your response variable, and this x is the predictor variable. This is just a model for like a simple linear regression. So we have what we call before we were talking about what we call SSE, SSR, all of that stuff. We're talking about this. We have SST, sum of square total.
That's the SSTS. Yeah.
Yes, we have SSR, sum of square regression, and we have SSE, which is sum of square error.
Error.
Now, so this one means this one is calculating like the difference between the observed value and the mean of the data. So let's say we have a particular X, let's say uh, price of oil. It's going to calculate what's the difference between each axis minus the mean. Let's say these are X. We have a particular X, 2, 3, 5, 3, 2, and 1. Let's say the mean is X bar is the mean is 5. So SST is saying that is now X minus
Hello?
X. Can you hear me?
Sorry, I was cut off for some time.
Can you hear me now?
Yes.
So if
I
this is
think we are
my
on the
X,
verge of explaining SST.
okay. So if this is my X is my independent variable, I just have one of them, and these are the values there, and this is the average of this value. So SST is just saying X minus the mean all squared. Take the sum. As was the trying to find the distance between the observed value and the mean. So that's what SST is saying. And also SSR is saying that what's the distance between
This like variation.
no this is not into this, but this is wrong. Sorry, it's not X, it's actually Y, not X.
Okay.
It's Y, not X. So the difference between the observed value, which is our Y, minus the mean of the observed value, which we are trying to predict. So, but SSR is saying what's the difference, what's the sum of square of the difference between the predicted value and the mean, all square like this. The difference between the predicted value and the mean. For SSE is sum of square error, which is trying to calculate the sum between the observed value and the predicted value, all square. So don't let me use bar, let me use cap instead of bar so that you will not get confused. The Y cap means the predicted value, Y bar means the mean.
But
So
in all of these, the mean is still the same throughout.
the mean of your observed value is different from the mean of your predicted value. So this one is
Mean different levels.
the observed, sorry, this one is the observed, difference between the observed and the predicted value. Take the square. This one is difference between your SST is difference between the observed value minus the mean of the observed value, whereas SSR is the predicted value minus the mean of the predicted value. Do you understand?
Yeah.
Okay.
I get for R, I get for T, but that E, I don't really get it.
This SSE.
The arrow aspect, yeah.
The error part is this guy. Don't mind this is not it. This is like SSE. This is sum square regression. That is that we did that, and that the difference between the predicted value and the observed value square. That's SSE. Do you get?
No, you have confused me.
This is our observed value.
Yes.
When we now use the model, we predicted this, but this is actually the actual value. But this is what we predicted. By the time I take this minus this, like the observed value minus predicted value for every one of them, I square it and I sum it. That's what we call. That's when you talk about SSE. That's the SSE. That's the sum of square error. That's the error term. You understand?
Okay, so it's not the SSR.
No, it's not the SSR. This one is sum of square regression. This is sum of square total. Okay. So it's that the best fit line is obtained using the method of least square, which takes the line with least possible sum of square error, SSE. That's what I explained that time. That is the one that forms the basis of your line of best fit. So the one with the minimum error is forms the best model. So during the estimation of the value of y, the slope can be calculated by multiplying the correlation between x and y with the blah blah blah. We are going to see this formula in the next slide. Also, I just your English. You don't see it in this slide, you see it in your material. So, but then, so the y-intercept b of the best line is obtained by subtracting. You might not understand this one, but let me explain here. So let's say this is your. Hello, Mary, can you hear me?
I can
Let's say
hear
Yes,
you.
man, I can hear you.
Okay. So let's say this is my model y is equals to b, which is my y-intercept plus mx, where m is my slope. To calculate your b, I will now say b is equals to y minus mx. But actually, my b is going to be y bar. My b cap. This b is m of this b. This one is like what the estimate I'm getting. So it's going to be my y bar minus mx bar. So this is the formula to calculate your p, to estimate your p. So with this formula, it means that I would have gotten what m is, right? I would have gotten what m is before I can use this formula in that regard. We are going to see that as we proceed also. So this is how you're going to calculate your p. So do you understand? Do you understand?
Like M being the coefficient.
M is the gradient, B is the y-intercept
Gradient.
or
Okay, like
slope.
triangular distance.
Like what?
When you do it, like when you draw y-x-axis, that triangular, the gradient is T aspect.
Yes, exactly.
Okay.
Okay. So simple linear regression. So simple calculators are not fit for large and complex calculation involved in linear regression. Blah blah blah. So there are some necessary factors that you will need to calculate some stuff, maybe SSR, SST, and all of that. You need your x. Your x is going to be given. This is your maybe your y. Your x squared. You need your y squared. You need your xy. But this is just they're just talking about the basic things you need if you are to be doing this manually. But if you are using R, you don't all these calculations, R is going to do that for you. You don't need to bother yourself. You're just talking about some basic calculation that you are going to be making if you are performing linear regression. So So how do we make use of all these formulas? So that's where we come to this place to, if you want to find so the famous five functions are used, which is all of these guys. This that you have calculated the x, y, x square, y square, and xy is used in this formula. So one of the calculation in relation is calculating of corrected sum of square. The formula for calculating sum of squares of x, as SSX, is now summation x squared minus into brackets summation x all squared over n. But if I'm doing for summation xy, instead of it to have x squared, I will have xy here. Then instead of it to have summation x squared, I will have summation x and summation y then all over n. This is calculation of sum of products, sum of square products x and y. But you don't need to bother yourself about this one. You might just it's simple to just catch. You can see that this one sum of square of x, I have x squared. Sum of square of xy, I have xy. Here, sum of square of x, I have summation x all squared. But instead of me to have summation x also, because this one is x 2 times, this one is now xy, so I have summation x and summation y and state all over n. So if I'm doing SS, maybe SSY, this one is going to be y squared, this one is going to be summation y all squared. So it's basic. So you can see that this SSE now, can you see SSE now? At least sum of square error that I talked about here.
Yeah, you can see.
That is here, your SSE. So that's your SSE. So which is your actual value minus your predicted value. So moving to the next slide. Now, trying to build a linear model, we use the LM function. Use the LM function. So in here, we are trying to build a linear model between count and speed. So from the data called FW. So in this function, you have your response variable is going to be the one. If you're using the formula method, your response variable is going to be the one at the left. Then after the tilde sign, you have your x. Are you with me?
Please come again.
So if you're using the formula method to build a linear model, you put LM, which is the function you're calling to build the model. Then specify your y. If you're using the formula method, this is going to be your y. Then after the tilde sign, which is this sign, you have your x. If you have more than one x, you can say, let's say you have speed plus distance. I'll have speed, then I'll put plus sign, then put distance. Then I'll say comma, then specify the data I'm calling it from. Say data is equal to FW. So for instance, if I want to build a linear model with the iris data sets now, so I'm going to do something like this. So I have this iris data set. I want to do linear model between petal width and petal length. And I can say iris, I want to call the name, say iris.lm is now equals to LM into square bracket and sorry, two brackets. Then my y, I want petal length to be my y. I specify petal dot length, which is the name of my y. Then I'll put the tilde sign like this and specify my y, which is petal dot width. Then I'll specify my data, which data am I using? Iris, like this. Then I'll run it. So it has built my model for me. If I want to see the summary of my model, I can use the summary command, say summary iris.lm. If I should run this, you have this result. So you can see here in this summary
Yeah, I have a
command.
question.
What's the question?
Yeah. Okay, I understand the Iris LM is the name of the model that you're trying to. Then the LM petal dot length is what is it?
My
I know it's the Y
yes.
variable. But I don't get why petal. Like, what's that?
It's the name of the column that I'm using on my Y. I'm using this petal dot length column.
Okay,
Petal dot
that's
length.
okay.
And I'm taking this one as my X. You understand?
Okay. Like why that the width is the X. Yeah, that's yeah.
Yes. So the
Okay.
summary, the summary command given is, so it first of all states the formula that I use, which is this. Then it gives me my residuals, my coefficient. You can see the coefficient here. You can see that this is the estimate, like your your b, your y-intercept, and this is the slope accordingly. So this is the slope. So your m in this case is this. Your m in this case is this. If you want to verify this whether it's correct, you can use that formula to find out b. What do we call the b? What do we call the b that time? You said b is what? Y bar minus mx bar. Let's try and check that. So I want to say b is equals to y bar. That will be the mean of my y bar is what? That will be the mean of my y, which is better than 10. So I'll say mean of iris ampersand separate dot so better dot length, which is my y. Then say minus what? M times x bar minus m times x bar. So I'll put my m here, 2.22. So let's use this m, 2.22994 times mean of what? That's our x bar, mean of our x, which is beta dot width. So that is ampersand beta dot width. So let's run this command now. Let's see whether we are going to have this value that is here. So let me copy. You can see that I have exactly approximately what I have here. Do you understand?
Yeah. But did our formula say mean? I didn't know there was a mean of y.
Yes, that's the formula. Translate y bar minus mx bar. Y bar is mean of y. X bar is mean of x.
Okay. I was looking at the first one.
No, not that. This one. So this gives you the summary, and this one is just to say, okay, it shows you the details of the name of the maybe entries that you have in that model. For example, it's going to give you call residuals, coefficients. So let me run it so I can see names of iris of LM. And so it give you coefficient, which is the name of this guy, residuals, effects, call. These are the things that are inside the summary command. So just give you the names of what is in this model. So if I run this names command on the iris data set, it's just going to give you the column names or the header of the iris. So if I run names of iris now, for example, you can see it gave me, okay, separate length is part of the column and separate width. So it just give you the name. So that's just the intuition. You should get what that is right now. You understand?
Yes, I get.
Okay. Also, so this one is just a said fw.lm after coefficient ampersand coefficient. This is just to get the coefficient of the regression, which are your slope and your what y-intercept. Where you can actually find that when you run the summary command, you can see that. But if you want to just see only the coefficient, then you can do this. Also, you can use this function to get the coefficient. Also, that's coef of the model you use. If you need the confidence interval, you can use this conf functions on the model to obtain the confidence interval of of the model. So do you understand what the intuition of confidence interval?
Is what did you say?
I said, do you understand the intuition of confidence interval?
Please refresh our memories.
Please, oh, I don't know.
I don't know
Wait,
whether
did you say
there's.
it before? Did
You
you say it
said
before? Did you say it
I've,
before?
I've talked about it before, but maybe not in this class.
Oh, okay. Because I'm just hearing.
So I think
I was wondering
did
whether
this.
it's something you said I didn't get.
uh, so let me try. Let me go on the confidence scale. Confidence iris LM. So so you can see here, this is the confidence interval for the intercept. It falls between this and this. This at 90. This is like at 5% confidence interval. So this is the guy for the gradient for what, for beta dot beta. That's the gradient of your model, your M, and this is your P. So let me show you the coefficient again. So I'll use the F function for the iris dot what, dot
Mm.
ln. So this is the coefficient. Can you see 1.08, 2.22? You can see that this coefficient falls in this interval. You can see that this beta dot split also falls in this interval. So
Okay. So
the
this is like a test to see whether you are close or something.
so this is just saying that I am like 95% confident that my intercept falls in this range. So we are going to have an exact, I'm going to have an exact value anyways. Also, I'm 95% confident my intercept is, my gradient is going to also fall in this range. It's just like say you want to predict now that if you should in June, and someone should predict that rain is going to fall in February, who is going to uh, be rest assured that that thing is going to happen? Obviously, the person that predicted in June, right?
Yes.
So if the probability of the person that predicted that rain is going to fall in June can fall between this range, say the probability is going to fall, probability lies between 0 uh, and 1. The person that predicted that rain is going to fall in June, probability can be between 0.8 to 0.9, because rain usually fall in June very well. But the one that predicted in February, probability can be between 0. Say say 0.3 and what, 0.9. You can see that the first guy is closer because that thing is likely to happen. But this one, the interval
Yeah, right.
is wider. It's just to accommodate that I'm not too sure. Make I no go fuck up. So 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 the gap is wider because what is actually predicting is out of this one, because it's not likely to happen. So you gonna have a wider interval. So to come to some decision, you use what we call level of significance. So if I increase the level of significance in this result that I have here, it said at 95%, uh, I'm 95% confident that my intercept is going to be between this range. But if I increase it to like 99%, 99% means I'm trying to say I'm very sure, but for me to be, I have to increase this interval. Like I have to widen it that I'm on like 9% is much. Let me widen my interval small and say but by the time I widen the interval small, I will like at least this intercept will fall in this range. So the higher the level of significance, the wider the interval is going to be, or confidence interval is going to be, so that to be able to still keep that, how do I want to put it, as certainty that this guy should still be true at this level. So we use these things to come to some decision when you're doing some kind of hypothesis testing. You can say, okay, let's say for example, you see that average is 6.5. 6.5. Then someone can come and say, okay, no, you are wrong. It can't be. It's greater than 3.5. Then you come and do some testing. If you test at 95%, at 5% level of significance, it means you are saying that at 95%, that you are 95% sure that null hypothesis, that is the average GDP of students in Nigeria is 3.5, that is going to happen. If I'm rejecting, if I'm accepting that fact that thing is true, if I should increase my level of significance to 1%, that is, I'm 99% sure. Then, if I'm still accepting at 99%, then it will actually be valid that I think you are true that at average GDP of students in Nigeria is 3.5. So the larger, the higher the or the smaller the level of significance, or the level of assurance, or the higher the level of assurance, then the rest assured, or you are that this thing is actually true. So we talk about this in hypothesis testing, though we have talked about this before, but I think you should get the scope of what I'm talking about, so I can move on now. Can we move on now?
Yeah, can move on.
Okay, so now talking about stepwise model building, I said we have forward stepwise regression, we have backward stepwise regression. Now, forward stepwise is that I want to find independent variable. I'm just predicting one dependent variable, one, but I have so many x's up to 10. If I'm doing a forward stepwise regression, first of all, I will start with the x, one particular x that's highly correlated with my y. So I'll start with that guy. So I'll build the model with that particular x. Let's say that particular x is x1. So I'll build a model y against that x1. But I have like 10 independent variables I want to consider, but I'll start with that x1. Then I'll start adding variables to it, depending on whether it improves the model or not. But backward stepwise deletion is, first of all, I'll insert all those 10 independent variables, I'll put them inside the model. Then I'll start deleting based on the model that does not improve. Get the logic? Do you get the difference between the two?
No, I'm not really clear.
So let me put it this way. You have a project that want to e-transact. So you have 10 employees. The dependent variable, what you're trying to predict is the efficiency of the outcome of the model, the efficiency of the outcome of the model. Okay, you have a project at hand. You have 10 people that are available that we can assign to that project. Maybe very, very skilled in that thing that we want to do at each transact. So I'm talking about forward stepwise now. So let's say Petra is the one that is very, very skilled relating to what we want to do on that project. I'll first of all put Petra there. Then I will start adding some employees to that project. So I will look at, okay, let me add Mary. No, I first of all put Petra to that project. Then I will see the efficiency of the project first. Then I'll not check. Okay. What if I should add maybe I'll check if I should add milk to this thing. I think this project, this efficiency of this project is going to increase. So I'll add milk. Then I will keep adding till I see that if I should add another person, it does not really change the efficiency of this project significantly. Then I'll stop adding. Then maybe it's just 5 people that optimizes the efficiency of the project. Then it's just I will stop at that 5 people. That is called stepwise regression. Do you understand? Do you
Okay.
understand?
Mm.
Now, the backward stepwise division is that those 10 people that are available for that project, I will throw them to the project. Yeah, you guys should go. Then I will start monitoring and see, let me first of all remove one person. I will see whether if the if the efficiency of that project does not significantly reduce, are you with me? I will take another person again that I see that probably is not really adding too much. I'll remove that person. I will now see again. Is this thing, is it increasing the efficiency of the project or not? If it's not adding up, I'll remove that person. Then I'll keep removing till I have a number of people that actually optimizes the model. So that I won't just have everybody there, just there. Maybe some people are not even not working, are even not working, they're just there for nothing. They are not even improving the project. Do you understand? Then I'll do that. So that's backward stepwise division.
Yeah.
Okay. So so uh this so you use the add one function for forward stepwise regression. You know, forward stepwise regression, you start with one independent variable, then you keep adding one, and so you also have drop one. So for the backward stepwise regression, which means first of all, put in all the independent variables, then keep dropping till you have an optimal model. So if you want to use the add one method, add one function, you put the model, then it says scope is equals to MF, which is like the data you're trying to consider in this case. MF, okay. Uh, let's see how this actually goes. Let me go to the next slide. So let me see. I don't think they're not really bringing that stuff here. So I built a particular model called mf.lm. So mf.lm here, and I do the add one function here, specifying the model, putting the data here. So you are going to see a particular table as a result. That's what you are going to use to.
Sorry, does LM means linear model, or it's just?
Yeah, LM linear model. Yeah.
Okay.
So I'm saying, okay, add one, this model, scope, this data, test. I'm using a features test in this case. Sometimes it can use some particular test by default. So this one, I started with a particular variable called, okay, you didn't see where I built the model here. So I start with one person and I keep adding and stuff like that. And this is the second one here. The second one here, I built a model with a particular variable y. Then I'm building it with what? You can see after the tilde sign, what did you see? You see a full stop, right? Data is equal to mf. This means that build this model with variable y and all other variables in that data. That's why I have full stop here. It means the build length with every other variables you can find in that data set. So if I have like 10 variables in that data set, the length is going to be built with the other 9 variables. Do you understand?
No, I don't get it.
So let me show you what I'm talking about. So let's say I want to use the iris data set to build a linear model now. So I will, iris contains 5 variables, but the The fifth one is a categorical variable, so I cannot use it. So I'll just exclude that one. So I'll say iris is equal to iris, the first four variables. Okay. So let me show you the head of iris now so you can see. You can see you only have four variables. See sepal length, beta, sepal width, beta length, and beta width. So I want to build a model using beta length against every other thing in this data set. So I will say, instead of me to specify beta width, I'll just put a full stop. So it means this is going to be beta length with sepal length, sepal width, and beta width. That is the three other variables.
All of them, the rest
Yeah,
of them, like
exactly. So let me run
that's
this
what
now.
dot and comma means.
No, that's what the stop means. That's what the stop means. The comma is just comma. I want to specify another thing after the comma.
Standard.
Yes,
Okay.
exactly. So let me run this now. So if I see this, check the summary of the model now, you see that you can see that you have sepal length, this one x, this another x, this another x. That you have three of them. So that builds the model using these three x's. So that's what that means. Now, here I built the model. Are you saying something?
Yeah, like three of them as against beta length.
Yes,
It's like
exactly.
transposing something,
So,
comparing it.
so I'm building this my y. So I have three x's, which is this, and so this is a multiple linear regression model. That is. So that's what they did here. They built length with all other columns that's in this data set MF. So now they wanted to use the drop one to do a uh, backward stepwise division. So I'll say drop one, specify the model, and specify the test. I don't need to put the data, the scope here. So the reason is that all the variables I need in that instance is already in the model. So it's going to know, you are going to know of which one you can draw because all the variables is already inside the model. The reason I'm putting scope is because MFA is that I'm only building with one variable at first. So I want to consider other variables in the data that I can add to the model. That's why I'm adding this MF so that it can tell me which one I can add to the model in that case. So let me go back to this guy and run the drop one function. So I'll say drop one. I'll specify the object. I don't put scope. So iris.ln. I can put maybe using this test to the features test. So I will have this result. So I will have this result. So with this result now, this is the intercept. That's why this one is none. So you forget about this one. Now we have this result. So in this guy, you can use whether the RSS or the AIC to come to a decision. So how do we come to the decision? We check for this sepal length. For these three variables, sepal length dot sepal dot length, sepal dot width, beta dot width. Which one can I drop to optimize this model? Which one can I drop to optimize model? Then I can check what we call this RSS or this AIC. But if you look at it, the smallest RSS also form the basis for the smallest AIC. The highest SS and RSS also form the basis for the highest AIC. So whether I use RSS.
Let me grab my charger from my system, please. I don't miss out of this thing.
Okay.
Thank you.
I could finish 2 or 3 sessions.
Okay, I'm back. Thanks.
Okay. Uh, can you hear me?
Hello, you can continue.
So, okay. So here, so what this one means, this is like residual sum of square. It's called residual sum of square, RSS. So the one you should drop, the one you should drop. First of all, let me even ask you, uh, which one do you think we should drop based on this guy now? Which one do you think we should
Okay.
drop?
SEPA with.
Okay, separate widths. So why do you think we should drop separate widths?
It's other way reason. I just checked and saw that it's different from the other figures, and it's not as close to the other two, like the way the other two are close to each other. That's just what I use.
Mm,
It's not arithmetic reason to it.
so, so the reason why I would say we should drop the separate width, separate width. You are right. You are right. Okay, but let me ask you. I don't know whether you are right. Or just let me ask
Maybe
you. Maybe, what do you think we should do?
this guy is jonesing me.
Mary, are you there? I don't think Mary is with us. So you're actually right. So separate width. The reason why we are going to be removing separate width is that
Okay, I can't hear your voice again.
you can hear me
Hello.
now.
Okay, yes.
So because of the lower the RSS, the lower this guy is adding to uh, it's not really adding value to this guy. So it means that it's not really adding value to this guy in this regard. So that makes separate with the guy we should drop. So that makes this guy the guy we should drop in this regard. So it means we are going to build, the thing is now we are going to build the model now without the separate weight. So it means you have to rebuild the model. So we are going to write this and exclude separate weight. So we're just going to do this. I'll copy this now. Then I would run this. Then instead of dots, I will specify the one I want to put. So I will be putting separate weight now. So I have to put separate dot length, and I will include better dot width. Better dot width. Then I'll build the model. Okay, so I'll build this guy. So let me run this command again. So running this command again. If you look at it now, which one do you think we should remove? Which one do you think? So we are going to be removing this guy. So we are going to remove this guy at this stage, and this guy is what is going to be left at the end. So why do you even say that this guy is, why do you think that this guy was the one that is left to optimize the model? If you check your correlation matrix here, you can see that beta width, which is the guy we are leaving behind now. If you check the correlation of beta width and this our y, which is beta length, you can see the correlation is very high, 0.96. So it forms the basis that this guy is going to actually even make
Do better.
do better. Yeah, exactly. Do better. So but hold on. Let me see. Okay. Okay. So the same thing if you want to do with add one. So let's say you want to do add one. Want to do add two. So I will build the model with just starting with one variable. So let me run this model now and build this with just beta.with. Then I'll use the add one to keep adding and see how we are going to use that to select the variable you should add into the model. So let me run the
Hello? Hello?
I think something is wrong with Emmanuel's network.
Oh, okay. How are you doing now, Mary?
I'm fine, I'm okay.
Nice. I'm
How
in
are
class
you?
today. Mark my register.
I used to be in class now. Just
As
that
in,
I
you're
called.
not saying me, I'm in class, so mark my register.
Okay. Like Emmanuel has gone off the call. So this is the end of our class. Let me stop recording.
Okay, this 352.